Hi, this is a class on Grand Canonical Ensemble. This is for my MSc students of SEM 2. By now, we have learned about the distribution function of the Grand Canonical Ensemble, and in my previous lecture, I forgot to specify, although I have defined that there is a quantity called z, which was exactly equal to e to the power minus of mu, and that was defined as e to the power minus of alpha. Sorry, it was not mu, it was minus of alpha, and that was where alpha was the Lagrange's undetermined multiplier, and this can be called as the fugacity of the particular system under. Now, this parameter, which is basically a measure of the chemical potential, because we know that alpha is minus of mu by kT. So, this is called the fugacity. So, now the prescription for actually evaluating the different thermodynamical parameters under the grand canonical scheme can be laid down, and those are, suppose we have this q potential, which was defined as equal to ln of summation of e to the power minus alpha nr minus beta es, where s, and we had written this to be equal to actually ln of r comma s. So this would give us r and z to the power r, and this was written because this would again be written as summation over s e to the power minus of beta es. So this part can be called as the canonical ensemble. So one can write this as ln of z to the power r, where z is the fugacity, and this is something which can be called as q of nr, which is a function of v and t. So this can be called, this part can be called as the canonical partition function, as we had already partition function. Okay, now we can call this whole thing as something like, I would like to define as a q, where this q is a function of z, v and t, and this q, double q, can be called as the grand canonical partition function. So once this q is calculated for a given problem, then we can arrive at the different thermodynamical parameters. How? Now we know that this small q is basically ln of this capital Q, okay, and this is written as PV by KT. So from here one can very easily define V KT by V ln of this grand canonical partition function. Similarly, one can define the number of the particles. So P, we can say P as a function of Z V T in the grand canonical scheme can be written as KT by V ln of grand canonical partition function. Similarly, how about N, average number of particles, that can be written as minus of del alpha of ln of summation e to the power minus alpha log natural of alpha nr minus beta es. So this can again be written in terms of alpha was basically equal to minus. So from here we can write alpha to be equal to minus of mu by kt. We know that. So we can write this as equal to kt del mu of ln of summation e to the power, okay, this can be called as ln of q, or you can call this whole thing as del q del mu, where q is the q potential. And this can again, so once q is determined, the q potential from the canonical partition function, so del q by del mu, and that can again, if you know mu in terms of z, so again you can write mu to be equal to kt ln z. So del mu can be written as del z into del z del mu, which is basically equal to 1 is equal to kt by z del z del mu. So z by kt, so del z del mu, okay. So del z by del mu is equal to z by kt, 1 kt by z del z del mu, okay. So del mu is equal to z by kt into del z of, so we can just substitute it over here. We can write z del z of q. So del z del z, so this is again the second prescription. So this was the first prescription for calculating the pressure. You can calculate the number density as a function of zvt to be equal to z del z of ln q. Similarly, one can arrive at the average energy, which was defined as E bar, which was equal to minus of del beta of q. Okay, so beta can be written again, alpha by beta was equal to one can again write beta in terms of temperature. Okay, so one can write del beta in terms of temperatures. So this can be written as t square del t of kt square. There would be a k function kt square del q del t. So the average energy can be written as from here, the second prescription. The third one, you can write u, which is equal to E bar zvt in the grand canonical scheme, to be equal to kt square del q del t. Okay, so these are the three things. You can even arrive at the rest of the thermodynamic parameters, from where one can very easily arrive at the Helmholtz free energy, which is basically equal to G minus PV. So that would be equal to N mu minus PV. One can get the value of mu from here, KT alpha, which is equal to ln z. So this would be equal to alpha. So mu is minus KT alpha, which is equal to minus of KT ln of z. Alpha is kt of alpha is ln of 1 by z. So this would be ln of z. So this can be written as n kt ln of z, and pv can be p V is kt ln q, so this would be written as kt ln grand canonical partition function. So one can write again minus of kt ln of grand canonical partition function divided by q by z to the power n. So one can define the different thermodynamic functions. One can even arrive at the entropy, which is equal to U minus A by T. So from here U and A, you can arrive at the relation for the entropy. So let us try to demonstrate a simple example of a classical ideal gas, because that we would be using for some time later on. So let us do some mathematics by applying the grand canonical formalism to the case of classical ideal gas. So first of all, let us consider the case of a classical ideal gas, and we try to demonstrate the scheme of grand canonical ensemble on this classical ideal gas. We remember by now that the corresponding canonical partition function, single particle function for a classical ideal gas, was given by V by h cube twice by mkt to the power 3 by 2. That was the classical canonical partition function, which can be written as V of some function of t. I am writing this in general form, some function of t, because I am now going to claim that for n particles, so this was a single particle partition function, and now for n particle we have qnvt to be equal to q1 to the power n divided by n factorial. Now this particular relation doesn't restrict in any way the presence of the interaction between the particles, which is absent in the case of classical ideal gas. And if there happen to be any kind of interaction, particle-particle interaction, that must be reflected in this Q1 in the grand canonical scheme. The second thing about this particular partition function expression is the n factorial, which actually represents the indistinguishability of the particles. Because the particles are indistinguishable, so we have to divide the n particle partition function by n factorial, because those microstates are not going to add up to new number of microstates. This concept of indistinguishability is closely related to the phenomena of non-localization. That is, if the particles are localized, then we can distinguish them, the particles, as we did in the case of statistics of paramagnetism, you remember. So these are the two things which must be kept in mind, because we would be using those concepts later on. So interparticular interaction must be reflected through Q1 if that is present, and the indistinguishability of the particles is expressed by dividing the n particle canonical partition function by a n factorial. Okay, let us now try to use the prescription which we just mentioned now. Okay, so the first thing is, what would be my Q potential? Q potential is nothing but equal to ln of grand canonical function, which is a function of zpt. And what is Q? Grand canonical partition function is basically equal to summation over n, and then there was a fugacity factor, so z to the power n, and then there was a canonical partition function which was q1 to the power n by n factorial. Now what is q1? q1 is equal to vft, so we can write it z to the power n vft some function of t whole to the power n by n factorial summation over n. So this is nothing but equal to z vft whole to the power n by n factorial summation over n, which can be written as exponential z vft, because as we know that e to the power x is summation of x to the power r by r factorial summation over r. So this is exponential z vft, and that simplifies our expression for q. The ln of q is going to give us ln of exponential of z vft, which is basically equal to z vft. And so we can define or derive the thermodynamic parameters, which are as follows. So the first thing is pressure. Pressure is kT by V into Q. So that would be equal to kT by V into Z V Ft, which actually gives us, so P, the pressure is V cancels out, Z K T F T. Okay. How about the number of the particles? Mean number of particles, which was defined as Z del del Z of Q. So that was equal to Z del del Z of Q. So that was equal to Z V F T. So immediately from these two equations we can say, we can arrive at the ideal gas equation, which is P is equal to NV, P by KT is equal to NV, P by KT is equal to NV. So that gives us P is equal to N by V. So PV is equal to NKT. So from these two equations we can arrive at the ideal gas equation. We can equally go on arriving or deriving the value of the internal energy, which is basically equal to kT square del Q del T. So that was equal to kT square del Q del T. So that gives us kT square Z V F prime T, and you can define the entropy and the Helmholtz free energy and so on for an ideal gas. And that can be left as a homework. You can do it for your own. Okay. Now we would like to talk about the fluctuation in the number density and the energy in the case of grand canonical ensemble. Why? Because just now we have seen that the thermodynamic parameters tend to remain the same for all the cases starting from microcanonical ensemble to canonical ensemble to grand canonical ensemble. So why, in spite of striking differences between this ensemble theory, because in the case of microcanonical it was NV all constant, in the case of canonical it was energy which was varying from 0 to infinity and NV remaining constant, so temperature was added as a parameter which remains constant for varying energy. And finally, in the case of grand canonical ensemble, where even the number of the particles are varying from 0 to infinity with the energy 0 to infinity. So here in the case of grand canonical ensemble, we have two variables which are varying. One is the number of the particles varying from 0 to infinity, energy varying from 0 to infinity, and for that we introduce two new parameters. One is the Z or the mu, chemical potential, or Z, the fugacity in the case of grand canonical ensemble, and for varying energy we have the temperature which remains constant for a given situation under equilibrium. So the basic reason for all arriving at the same thermodynamic parameter is nothing but the the reason again remains the same as we did in the canonical ensemble. It is the fluctuation. How does the fluctuation in number of the particles and the fluctuation in energy depend as you go on increasing the number of the particles? That is the reason for minimizing the, so as you go on increasing the number of the particle, the main reason, basic reason of all having the same thermodynamic result is that as you go on increasing the number of the particles, the fluctuation in the number of the particles, relative fluctuation in the number of the particles and relative fluctuation in the energy, both would be minimized because they vary mathematically as 1 by square root of the parameter. Let's prove that thermodynamically or mathematically. How can we prove that? So in the case of grand canonical ensemble, the mean number of particles is given as summation of nr e to the power minus of alpha nr. So the mean number of the particles for this is nr e to the power and e to the power minus of beta es, okay, r comma s divided by summation of e to the power minus alpha nr beta es. So how about taking delta n average del alpha? So what does this give? If we take another derivative, partial derivative of the mean number of particles, then what do we get? We get this to be equal to, so this is going to give us the first thing is going to give us this, so this is going to give us nr square, okay, minus nr square alpha nr minus beta es with the same denominator, okay, alpha nr beta es, and then this is going to again give us 1 by this whole thing square alpha, because this also contains alpha, so nr minus beta es whole square, and then there is a derivative of this, so this is going to give us again nr, so this is nr e to the power minus alpha nr, and there is all again the same term in the numerator, so this would be square. So what we can say is this is equal to minus nr square average, and this is going to give us, there is a minus and then there would be again a plus because there is a differentiation with respect to again alpha, so there would be another plus, so this would be equal to plus nr average square. So what we can write is nr or n average, okay, because of the definition, okay. So we can say that minus of del n average del alpha is equal to n square average minus n average square. So we can take the mean square fluctuation from here as delta n square, and this is something which has been taken with respect to constant beta and es, so we can write this to be at constant v and t. So beta, from beta we have t and v. So this is, so we have the mean square average to be equal to minus of del n del alpha, which is basically equal to del n average del alpha at constant vt, and this can be written, alpha is nothing again, alpha is equal to minus mu by kt. So we can write this minus mu by kt, so we can write this as to be equal to kt del n average del mu at constant v and t. And if we divide this by the mean square, this was the fluctuation in the number, so you have to divide this also by mean square. Okay. And now if we take the corresponding specific values, let us define, let v, small v is v by n average. This is the specific volume. So we have this delta mean square by n average square to be equal to kt by n average is v, so this would be equal to v square, v by, okay, and del of v by del mu. Okay. So since v is constant at a constant temperature, so we can write this to be equal to kt v square by v square, and there is a minus of v by v square del v by del mu, okay, at constant vt. So this is going to give us minus of kt, this and this cancels out, kt by v, and del v by del mu, which can be very easily arrived at. You can just, we know that the Gibbs free energy is given by A plus PV. So Gibbs free energy is A plus PV, which is equal to U or minus TS plus PV. So dg is du minus tds minus sdt plus, this is a simple thermodynamic problem, we have proved it previously. And from the first law of thermodynamics we know that du minus tds plus pdv is equal to dq plus mu dn. So first law of thermodynamics gives these three terms to be equal to mu dn, okay, mu dn minus sdt plus vdp, and the left hand side we know that this is equal to mu n, so dg would be equal to mu dn plus n d mu. So mu dn cancels out, and n d mu is this. So one can now one can just define d mu to be equal to small s specific entropy, S by N is specific entropy, and VdP minus S dt VdP. And if the temperature also remains constant, then one can define for T constant, T is equal to constant, one can define V to be equal to del mu del P, okay, at constant T. So substituting, so from here one can say that for del mu, sorry, okay, so del mu is nothing but VdP. So at constant temperature, del mu, so we can write d mu to be equal to VdP at constant temperature. So we can just define the fluctuation del n average square to be equal to minus of kT by V, and d mu is replaced by VdP, so this would be equal to 1 by V dP and dV. So this is nothing but, this part is the inverse of the bulk modulus of elasticity, minus of dP by dV by V. So that gives us isothermal compressibility. So we have minus kT by V and kappa T. This is isothermal compressibility. Now we can talk about this. So I have written the mean square relative fluctuation as what I have derived as minus of kT by V, 1 by V del V by, and this can be written as kT by V into the isothermal compressibility, where kT is equal to minus of 1 by V del V by del P at constant temperature. And we know that kT is basically inversely proportional to N, because that contains pressure term in the denominator. And so if one calculates the root mean square fluctuation in the number of the particles in the case of grand canonical in number density, okay, you can also call it number density, which is, this can also be written as delta n square average by n square average, because n is n by V. Okay, so you can write this as delta n square by n average square to be proportional to 1 by n, or square root, sorry, this is square root would be proportional to 1 by square root of n. So this is called the root mean square fluctuation. So we can see that the root mean square fluctuation in the number of the particles varies as 1 by square root of n, which is basically 1 by n to the power 0.5. Okay, so as the number of the particles becomes large, which is the case in the case of thermodynamic systems, so that's why our grand canonical system scheme converges to that of the canonical scheme and to the microcanonical scheme. But there are exceptions for this particular relation, because in the case, and those exceptions are in the case of phase transition, where actually the flattening of the isotherms occurs, and there the isothermal compressibility, this isothermal compressibility does not obey this kind of simple relation because of the flattening of the curves, flattening of the isotherms. And then you have different relation for, and the n could be even larger. It could be something like n to the power point, and there you need to always go through the scheme of grand canonical ensemble in order to deal with such situation, as we will see in our later course in statistical physics. Thank you.